In this video, I'm going to give you an overview of the material from Chapter 1 of our text, Fundamentals of Physics, 11th edition. And Chapter 1 is about measurement, units to be more specific. I'm only going to give an overview. If you want more detailed explanations, and I encourage you to do this, you should read the online book, specifically Chapter 1. Section 1 is about measuring things, focusing on length. Section 2 is about measuring time. And Section 3 is about measuring mass. So let me begin now with my overview of the main things you need to know. First, one of the things you need to be aware of is that we will be coming in contact with three different, what we call systems of units. The most frequently used system is called the SI system. That's SI stands for System International. And in the SI system of units, any length must be measured in the unit called meter, denoted M. Any mass must be denoted in the unit kilogram, kg, and any amount of time must be denoted in the unit second, symbol S. There is also the so-called CGS system of units, where every length must be expressed in a centimeter, cm, every mass must be expressed in a gram, g, and time is expressed in seconds, s. And then once in a while, we will use the English system, where the length must be expressed in the foot, ft, the mass unit is the slug, slug, and the time unit is the second. So those are the three systems of units we will be using in the order of frequency. SI used most, CGS next, English last. Here's an important tip, and if you can remember this tip, it will save you lots of lost points on quizzes, homework, and tests, because it is one of the most common mistakes with units. And the tip is that you cannot mix different systems of units. In other words, when you are in a given row, such as the top row with the SI system, you must work only within that row. Every length must be in meters, every mass must be in kilograms, and every time must be in seconds. Okay? You cannot mix rows from this table. In other words, in a given calculation or a given problem, you can't have a length in meters and a mass in grams, or a length in feet and a mass in kilograms. If you mix different systems, you know you're going to get the wrong answer. Okay, so those are the three systems of units we'll use, with SI being by far the most commonly used. Another idea that comes up in this chapter and throughout the whole book, the whole class, is the concept of mass density. So I want to give you the definition of that now, because we'll need it to solve problems in Chapter 1 and problems in other chapters. So what is the definition of mass density for a substance? It is quite simply the mass per unit volume of a given substance. Remember, per is another word for divide. So mass over volume of a substance. We have a symbol for this quantity called mass density. And in physics, the symbol, and we must stick to this use, is the Greek lowercase letter rho. And here it is. It looks like a kind of a letter P, but it is not the letter P. It is the Greek letter rho, and it's kind of curved, as you can see. That's the symbol we use when we denote the density of a substance. The SI unit of density is mass unit, kilogram, over volume. Well, a volume is three lengths multiplied together, so the volume unit in SI would be meters cubed. Here's another tip. If a substance is uniform throughout, if it's the same throughout, and this sample of this substance has a total mass m and a total volume v, then the mass density rho is simply the total mass divided by the total volume. Okay, we will use this formula a lot. All right, something else you need to know from Chapter 1 is the metric system and the typical prefixes for the units in the metric system. And it's not just for SI, it's also for CGS. But every factor or power of 10 has a prefix, name, and a symbol. All right, so these are various powers of 10. And I've highlighted the most common ones. These are the ones that you should just know off the top of your head. Like 10 to the 6 is called mega, symbol capital M. So you could have 10 to the 6 meters, that'd be megameters. 10 to the 6 grams, that would be megagrams. Or 10 to the 3 is kilo, symbol K. So 10 to the 3 meters is 1 kilometer, or 10 to the 3 grams is 1 kilogram. Okay? Other common powers of 10. 10 to the minus 2 is centi, symbol little c. Right? So 10 to the minus 2 meters is 1 centimeter. 10 to the minus 3 is milli. 10 to the minus 6 is micro. Notice the symbol is the Greek letter mu. 10 to the minus 9 is nano. 10 to the minus 12 is pico. These are common prefixes in the metric system. You should know them. The other thing that you should know is how to do units conversion. We'll do that all the time. Okay? So I'll give you two brief examples. We call it, you use in this book what we call the chain link units conversion system. So for example, suppose I give you a certain length in meters, 150 meters, and I ask you how long is that in the unit micrometers. How do we make that conversion from meters to micrometers? Well, we have 150 meters. We're going to multiply, this is where the chain link comes in, by a link in a chain, because you could have multiple links if you needed to, where the quantity in the parentheses, this link in the chain, is equivalent to unity, to 1. And so I'm multiplying this number 150 by 1, so technically I haven't changed it. But this number 1 looks a bit odd. Well, it's going to help us change the units. It's this equivalency here that is equivalent to 1 is that 1 micrometer is equivalent to 10 to the minus 6 meters. That's just based on our table of metric system prefixes. Okay? 1 micrometer is equivalent to 10 to the minus 6 meters. I used the chain with the 1 micrometer upstairs and the 10 to the minus 6 meters downstairs so that the unit of meter upstairs in the 150 would cancel the unit of meter downstairs in the chain link conversion, leaving me with the unit micrometer, which is what I want. And then I just use my calculator. I divide 150 by 10 to the minus 6. Notice 150 divided by 10 to the minus 6 turns out to be very big. And here I'm expressing it in scientific notation, 1.50 times 10 to the 8 micrometers. So that's what 150 meters is equivalent to. It's equivalent to 1.50 times 10 to the 8 micrometers. Okay, that's a very basic chain link conversion. You must be able to do that. Here's a more challenging one that people can find tricky. A volume. Right? Suppose I have a box with a certain volume, and specifically its volume, its interior volume is 25 meters cubed. And I want to know what that volume is in centimeters cubed. How do I do the conversion? I start with the number I'm wanting to convert, 25 meters cubed, and I multiply by a chain link conversion factor that is equivalent to 1. All right? And here the chain link is 100 centimeters is equivalent to 1 meter. We know that's true from the metric system, so I'm multiplying by 1. But I note that when I write the units here, 100 centimeters is 1 meter, that isn't going to cancel the unit over here because I have a meters cubed. So I have to multiply the chain link conversion, or raise it, I should say, to the power of 3. Since this chain link conversion factor is equivalent to 1, raising it to the power of 3 is still 1 cubed, which is 1, which means I still technically haven't changed the value of anything. I'm just expressing it in a different unit. So 1 meter cubed cancels the meter cubed here in terms of the units. And so I take 100 cubed on my calculator. 100 cubed is 10 to the 6th power. You check that on your calculator. And then multiply that by 25. I get 2.5 times 10 to the 7 power. centimeters cubed. So that's another kind of conversion that you have to do, of volume. Okay? All right. Now, let me show you a typical, what I call Wiley Plus homework problem. In fact, I took this from the online book, Wiley Plus Reading in Chapter 1. At the very end of Read, Study, and Practice, you will find practice problems. This is problem number 26 in Chapter 1. And it's typical of the online homework that you will have to do soon. It exemplifies the kind of reasoning that you will need to employ. The problem goes like this. 1 cubic centimeter of a typical cumulus cloud contains 250 water drops, which we are told to treat as small spheres. And each drop has a typical radius of 10 micrometers. Water has a mass density of 1,000 kilograms per meter cubed. Question A. How many cubic meters of water are in a cylindrical cumulus cloud of height 3 kilometers and radius 1 kilometer? Here's just a picture of a typical cumulus cloud to demonstrate that this part of it here, which is the main part of it, is shaped somewhat like a cylinder. So this problem basically tells us to do a very physicist-like thing and model this shape as being a perfect cylinder. It's got a height of 3 kilometers and a radius of 1 kilometer. How many cubic meters, that's a volume, what volume of water is contained in this cloud? So I'm going to work this problem with you here in this video using my iPad, much the same way I would do if we were in a classroom and I had chalkboard available to me. So here now you should be able to see my iPad open, and I'm just going to be able to write on the screen of my iPad, and you'll be able to see it, and I'm going to demonstrate for you in this example 1.1 how I would go about solving it. Okay, so here's part A. The first thing I like to do in working an example problem is draw a sketch. So I'm going to draw a sketch of this cloud. A cylinder is circular in cross-section, and it's got a certain height. I'll draw a dashed line down through the middle, and an arrow here to denote the radius r. And let me come over here to the side and express what I know about that radius. It's 1.00 kilometers. Remember, a kilometer, kilo is 10 to the 3, so that's a 10 to the 3 meters. That's 1,000 meters, which I can also write in scientific notation. 1 times 10 to the 3 meters. For reasons that you'll see in a minute, I also want to convert this to centimeters. I will let you do that. You get 1 times 10 to the 5 centimeters. The other important dimension for this cylindrical cloud is the height h, which I'll denote with a capital H. I am told that h is 3 kilometers, 3,000 meters, 3 times 10 to the 3 meters, or 3 times 10 to the 5 centimeters. Okay, now, I know that if I could zoom in and see, I'll use a different color here, inside this cloud, and let me do it like a zoom, and if I could look in exactly 1 cubic centimeter of the cloud, that it has on average 250 spherical drops of water. And that means I can write down a formula for the volume of any one of those drops. Since they're spheres, there's a well-known formula for the volume of a sphere. Spheres are common in physics and because they're useful to describe nature. So we need to just know, or you can always look it up, right, the volume of a sphere if you know its radius. And that formula is 4 over 3 times pi times the radius cubed. So that r means the radius of each one of these little drops, which I'm told is 10 micrometers. That's 10 times 10 to the minus 6 meters. That's 1 times 10 to the minus 5 meters. Okay, now you have to think a little bit about what we want. We want the total volume of water. We're told that we can think of the cloud as having little water droplets, each being a sphere. We know the formula for each drop, the volume of each drop. So the total volume of water, just got to think about this a little bit. We've got to write down our work and label things clearly, would be the number n of water drops that there are, I'll call that n drop, times the volume that each drop has, which we'll use that formula up there for V drop. So now it just boils down to finding how many drops of water are there. Well, that's the number of cubic centimeters of cloud times 250, right? Because every cubic centimeter of cloud has 250 drops. Okay? All right, so now I have to have a formula for the number of cubic centimeters of cloud. That's a dimensionless quantity, just the number, how many. So I'm going to write another little word formula. The number of cubic centimeters of cloud is going to be the volume of the cloud in cubic centimeters divided by the volume of 1 cubic centimeter. Okay? That's going to be the number of cubic centimeters. Now, what's the volume of the cloud in cubic centimeters? Well, we're told to treat the cloud as a cylinder. Remember our picture at the top? So we need another volume formula for a common shape in physics and nature, a cylinder. Again, that's common, so you can either know it in your head or look it up. The formula for the volume of a cylinder is pi times the radius squared times the height. And I'm using the symbols from my picture up there, right? And the volume of 1 cubic centimeter is exactly 1 cubic centimeter. Sounds almost silly, but it's useful. Now note that when I plug in numbers for the radius, this radius, big R, and the height, big H, they need to be in centimeters, because I need the volume of the cloud in centimeters to divide by 1 cubic centimeter to get the dimensionless quantity NCC. So now let me plug in numbers. Okay, pi times the radius of the cloud in centimeters, 1 times 10 to the 5 centimeters. Don't forget to square that, times H, 3 times 10 to the 5 centimeters. Okay, I've got to move this up so that you can see it. Divided by 1 cubic centimeter. All the units between the numerator and the denominator are going to cancel, and I'll write down with some extra sig figs, because it's an intermediate step, how many cubic centimeters there are in this cloud. 9.425 times 10 to the 15. Okay. All right. Now I'm ready to work out the volume of water. It is, using my word formula, the number of drops, 250, times the number of cubic centimeters of cloud material, 9.425 times 10 to the 15, times the volume of one drop, 4/3 pi, times the radius of a drop, cubed. 1 times 10 to the minus 5 meters cubed. I will write down what I get. I get 9.87 times 10 to the 3 meters cubed. Okay? 9,870 cubic meters of water. And we have answered part A. Now, you may have to watch this part of the video a couple of times and try to absorb the kind of thinking that is involved here. Okay? Because it's very typical of the kind of thinking we'll do in this class. Notice it's basically this kind of counting and geometry and units. Counting and geometry and units. Okay? But it's the kind of thinking that physicists and engineers need to employ. Now, part B follows pretty quickly here. Let me go back to it and read it to you. B, how much mass in kilograms does the water cloud have? Okay, I know the volume of the water, 9.87 times 10 to the 3 meters cubed. Please remember I was given the mass density of water, the mass per unit volume, 1,000 kilogram per meter cubed. In fact, let's write that symbolically. Mass density is mass divided by volume. We're going to use that formula. We know the mass density of water. We know the volume of water in the cloud. So we're just going to solve symbolically for the mass, multiply both sides by the volume, V. Mass is density times volume, and we're just going to plug in numbers. So the mass density is a property of fresh water. Notice how I'm writing the units. 1,000 kilogram per meter cubed, and I multiply that by the volume of water that I just found that is in this cloud, 9.87 times 10 to the 3 meters cubed. Note the units meters cubed cancels. Multiply this out. Please don't go to your calculator for this. To multiply by 1,000, just increase this exponent 3. So it goes from 10 to the 3 to 10 to the 6. You get 9.87 times 10 to the 6 kilograms. That's 9,870,000 kilograms of water. That's over your head if you're standing under a typical cumulus cloud, which is pretty impressive, isn't it? Notice how you have solved for something that you probably have never thought about before, just given a little bit of basic information and then using some simple thinking. Okay? Almost 10 million kilograms of water over your head if you're standing underneath a typical cumulus cloud. So that is indicative of the kind of thinking you'll need to use to solve the homework problems from Chapter 1. And that's where I'm going to stop the video for now.